There are a number of networking terms you should be familiar with. First of all, LAN, Local Area Network. This actually refers to a network in a relatively small geographic area, like the floor of a building, or inside a lab, or simply a single building. In other words, resources are fairly close together. You have a small network, your computers are communicating with one another. We also have what's called a wide area network, or a WAN. Now that's exactly the opposite of a local area network. It's dispersed, it's widespread. Simple example here would be the internet. It's sort of the ultimate wide area network because it's worldwide. Maybe a business example, suppose you have an office building in Salt Lake City, Utah, Minneapolis, Minnesota, and New York City, New York. Well, you could have a local area network, a small network in each of these three office buildings, but they could be connected across the United States to create a wide area network for business communication. So local is just that, wide means widespread. There's kind of an intermediate form that you may hear mentioned too, and that's called a MAN, or metropolitan area network. That's simply a network that's spread around a single metro area instead of like a single building or worldwide or across the state. Now, there are a couple variations on networks that I'd also like to talk about, and that is the client-server and the peer-to-peer. I should let you know that this goes into more detail in the operating system course, where we're talking more about the network operating system, because these terms refer more to the operating system they're used. But just to give you a brief overview, when you're talking about networks, you have something we call resources. Now, a resources is something your computer can use, like a printer. You can get access to files, maybe applications you can run. Resource is a pretty generic term. It's just something your computers can use or get access to. In a peer-to-peer network, we have a group of computers, and any one of these computers can provide resources to the other computers. So in other words, any computer can have resources, any computer can request resources. They're peers. They're kind of on equal standing or equal status. The client-server network is very much the opposite of this. In a client-server network, the server has the resources. So the resources are centralized on the server computer or computers. You might have a print server. That would be the server that controls the printer. Or maybe you have a file server. That's a server that has a big hard drive and contains lots and lots of files. The clients are the computers that make requests for the resources. So in this model, instead of sharing resources between all the computers, we have a more centralized location for the resources, which means your servers need to be a little bit more powerful, and we have clients that are requesting the resources. Now, as I mentioned, we'll go into this in more detail in the operating system course, because how you set this up is somewhat operating system dependent. Different types of networks use different topologies. Now, the physical topology is the actual way the cabling is run. The logical topology is the message path, so a way a message runs through the network. The physical topology and the logical topology are sometimes absolutely identical, but sometimes a network will use a different physical topology from the logical topology. I have an outline of the different topologies here on the board. First, we have the bus topology. There's a single cable running down the center here, and the messages are sent back and forth along this single cable. The computers are attached to the cable on the bus. Now, if I address a message to a specific computer, that computer will pick the message up off the bus, and the rest of the computers will simply ignore it. In the star topologies, there's some sort of device in the center. Oftentimes, this is something we call a hub. So the messages to go from one computer to another need to pass through this central device or hub. One thing you might want to keep in mind, obviously the star topology is going to take more cable to set up than a bus topology if we're talking about the physical network. On the other hand, this is by far the most common topology in use today. Why is that? Well, the bus topology, it's a little difficult to add computers to this setup, and it's a little difficult to troubleshoot. If you think of this cable, this one long cable, as running through a building somewhere, maybe up in the crawl space above the ceiling, what happens if it breaks? Well, it affects all the computers on the segment, and you have to find the break somewhere up in that crawl space. On the star topology, there's one cable between the central hub and the computer, so it's a lot easier to isolate problems. Even though it takes more cabling, if this cable right here goes bad, I'm pretty sure it's that cable that went bad because this computer lost its connection and not the rest of them. So although it takes a little bit more cable to wire this particular setup, it's actually a little easier to work with, which is what makes it very popular today. Now the next one I have listed is the ring topology. In this setup, messages simply travel around the ring. This is used in a setup today called IBM token ring. And in this setup, there's actually a little token that you can use to send a message, and the token runs around the ring with a message attached to it. The mesh setup, I have two variations here, the full mesh and the partial mesh. Now honestly, you're probably not going to see a full mesh. In a full mesh, every possible connection is made between every single computer. If that strikes you as possibly way too many connections, you're right. This is going to become exceptionally expensive if you have a lot of computers. The advantage of this kind of setup, lots and lots of redundancy. If a line goes bad between those two computers, I still have a whole bunch of different ways to get from this computer to this computer. I could go through here, I could go through there, and so forth. So there's a lot of built-in redundancy. On the other hand, this full mesh is way too expensive to set up if you have a lot of computers. What you're more likely to find is a partial mesh. See, you kind of started with the mesh diagram, but you haven't finished it. This isn't as expensive, but it does have the data redundancy still there. So if I lose this connection, I haven't lost my ability to get from this computer to this computer. I can reroute it. This partial mesh setup is actually somewhat common for wide area networks when you have many sites linked, because it gives you some redundancy between sites. And then finally, the idea of a hybrid. A hybrid is simply a mix of the different topologies listed here. Media access control methods are all about how the messages are actually sent over the wire on the network. I have a couple examples here. These aren't the only type of methods out there, but there are a couple good examples to kind of illustrate the basic concept. The first one, CSMACD. It's kind of a mouthful. It's short for Carrier Sense Multiple Access Collision Detection. Now I've drawn an example bus topology here to help you understand how this works, because without a topology it's a little bit confusing. On this particular topology, the computers need to communicate. They need to sense the access. So this computer is going to kind of check and see if the line is busy. If the line's not busy, it's going to send a message out. All right? Now the problem with the collision detection. What if two computers send messages at very close to the same time? Well, you have a big old collision right there, and the messages are going to get garbled because two of the messages traveling on the same wire can potentially cause a problem. Well, that's what the collision detection is all about. If a collision occurs, the computers sense there's a collision, and they wait a little bit of time and they try again. So we're trying to sense whether or not the wire is busy, and then if we have a problem, a collision, we're going to try and fix it by resending the message. The other example I have here is called token passing. Now in token passing, there's actually something called a token that's necessary for sending a message. So we have a little token, and the token just kind of travels around the ring. Now if this computer here wants to send a message and the token is free, basically the computer grabs the token, attaches the message to it, and then that message can be sent around the ring to the next computer over here. Maybe it needs to pick up the message. But you can't send a message unless you have the token. And really that's the point of token passing. Notice that you're not going to have collisions in this scheme. So it's a little different media access control method. So basically what we're talking about here is how we're going to send the messages. And we've just given you two simple examples. A network architecture is actually more of a specification. In other words, there's more to your network than just the fact that there are cables. There's the hardware you're using, there's the kind of media access method that you're using, and so forth. Ethernet is a particular type of network architecture. This particular network, Ethernet, uses CSMACD as its media access method. We have a number of different variations, 10 base 5, 10 base 2, 10 base T. It's been around for quite a while. I have some graphics to help us understand some of the variations of the Ethernet architecture. First of all, 10 base 5. 10 base 5 is also sometimes called thicknet because it uses a fairly thick, heavy coaxial cable as its cabling. It uses a bus topology, so there's kind of a straight cable with everything hanging off of it, and individual segments of cable, or individual segments, can be run for a grand total of 500 meters. This is a much older architecture, and by the way, that's where the 500 comes from, or the 5. In the 10 base 5, it's the 500 meter distance. This is a much older architecture. It's not being installed in new installations anymore, but you may run into it if you're looking at an older setup that hasn't been upgraded. It runs at 10 megabits per second, so it's not super fast by today's standards. Now 10 base 2 is very similar to 10 base 5. This uses a wire or a cable, a coaxial cable, sometimes called thin net. It's also coax, but it's a little bit thinner and more flexible than the cable used with the 10 base 5. The 2 in the 10 base 2 refers to the fact that you can run a single cable for a grand total of 185 meters. They've rounded it up to 2 for 200, I guess. Anyway, you get the 185 meter cable length. This one also runs at 10 megabits per second, so again, it's not the fastest thing out there. And it also uses a bus topology. So the 10 base 5 and the 10 base 2 are really quite similar. Again, this is a somewhat older installation type, and it's not being used very widely in new installations anymore. The last of the examples here, 10 base T, we're actually using twisted pair instead of coaxial cable. Also, you can run each individual segment of twisted pair for up to 100 meters, but one big difference here. The physical topology is a star. There's a hub in the center, and you have the cables running in a physical star out of the hub, but the logical topology is a bus. This is the more common type of wiring setup with Ethernet we're seeing today, and actually even more common than 10 base T is to move towards something called 100 base T. 10 base T runs at 10 megabits per second, 100 base T runs at 100 megabits per second. Both of these use twisted pair, both the 10 and the 100. If you're going for the 100 base T, you need to use category 5 twisted pair cable. Now, one other thing you need to understand about the two coaxial setups, 10 base 2 and 10 base 5. The end of the cables need to be terminated. That's because we have a long bus architecture or bus topology, and this terminator at the end basically absorbs the signal and prevents it from bouncing back. Now, on a 10 base T network, you don't have to terminate the end of the cable because basically the cable terminates when you attach it to the computer.